Great. All right, so starting off the afternoon session, we have Roland Haas filling in for Steve Brandt, who's feeling a bit under the insufferably hot weather. Yeah, so he's going to tell us, Roland's going to tell us about the Cactus production interface. And take it away.
Thank you. All right, yeah, so as I said, I'm subbing in for Steve Brandt, who is planning to give this particular presentation. This is again one of these series of more in-depth tutorials for how to use the Einstein toolkit. So it goes beyond how to get started, it goes a little bit more details and tries to cover some of the things that are maybe error-prone if one doesn't quite know what one is doing. You can also find this one in the current local server. If you scroll it to the bottom, then there is one that says using the Cactus reduction interface somewhere here. And you can double click on them, and then you should see what I see right here now. Somehow managed to have that visible. Right. So there's two things in this notebook. One of them is just me chatting to you and explaining to you how this thing works, and I'm showing you what kind of Cactus functions exist. But it also has a section where it actually constructs a little bit of a thorn, namely a thorn that computes the center of mass of a distribution of matter on the grid. Strictly speaking, not the center of mass, but something that's close enough for purposes of, say, tracking the center of a neutron star to use it for regridding. That's a typical application that you would want to do with a reduction interface. Maybe you might have the distribution of density on the grid, and you would like to reduce that one to a single number reduction and use something like this. In this case, we wouldn't just reduce the mass, the density that would give you something like a mass, but you multiply the density by the x coordinate coordinate that gives you a dipole. If you integrate up the dipole value, you get the center of mass, basically. So that's one of the uses there. There's other things you could try and find the maximum value on the grid. Maybe you want to know the maximum error, maximum Hamiltonian constraint violation on the grid, or the minimum of the lapse, things like that. So basically everything that goes from much data on a grid to a single data is called a reduction. Called a reduction by, I guess, the fact that this is what is called an NPI. And these things are fairly very small layer around the actual NPI nodes. Pretty much all software infrastructures will have that in one form or the other. Right. So for those of you who want to follow along with the notebook setup, you'll see it's a little bit similar to the started tutorial. In that it first introduces a bit of magic and loads some Python helper packages, and then it actually untars the Cactus source code. So this is probably redundant because I think for those of you who already followed along for the writing at board or getting started tutorial, you've already done that, and I don't think it's anything else actually. It just gives you a checked out source code, and this is also precompiled, so it's fine. So let me see how long that takes. While this is expanding, up a little bit, I'll talk a little bit about what the reduction interface offers. So I said it is a means of taking the data that you have on the grid and reducing it down to single values. Okay. Exactly what you can do depends a little bit on which driver form you use. Mostly they offer the same functionality, but there can be slight differences. So typically the PUG and the Kirkwood driver, and the Kirkwood X driver as well, offer the same sort of functions. There will be a function to compute the minimum and a function to compute the maximum, but they're actually named differently. One is called min, the other one is called minimum. Similarly, you would find a set of norms. Norm 2 basically the weighted L2 norm, or just maximum norms over here that you can use to get an error. One thing to keep in mind is that anything that looks like a sum reduction naturally, but also the L1 and L2 norms, they actually take into account, at least for Kirkwood, the size of the grid cell that they're integrating for. So for any grid driver like PUG, it's very easy to do this. You literally just sum up all the values that you have on the grid points and figure it out. But if you want to do this in Kirkwood and you want to do it somewhat sensibly, if you, for example, summing up the density, what you actually want to sum up is some measure of the total mass, something like density times the representative volume of the cell. and all get added up. That's what the sum actually does. It is in fact the integral up to a constant scaling factor. That's the volume of the courses grid. So it doesn't know how much volume the courses grid has, but it knows that the finer grid cells have an eighth of the cursor one because they're half the size in each dimension, and so on and so forth. So that's what you get. So they are basically a Riemann integral of your data. So this is up here a little bit, so the whole thing is constructed such that if you were to do that sum reduction and you multiply by the volume of the courses grid cell, you drive to resolution to infinitely high resolution, you do in fact get back the integral over the density. Sum goes to density to integral the way it is. Okay, let me see. If my uncharring is finished, now I have a fresh copy of Cactus in there that I can click. Okay, please do interrupt me if you have any questions, either online or in. Okay. So there are a number of ways that you can use reductions instead of Cactus. Simplest way is you just need to know what's the maximum because you want to plot your error, your constraint violation. You can simply ask the output system to produce the maximum reduction and write it to a file. So there is the Kirkwood IO scalar thorn that can write reductions to a file, and in buckets IO basic. And these you can just write out time series of these quantities, and you can typically do that for constraint violations, minimum and maximum of the density, and the lapses. That's the easiest way because you just put this into your parameter file, you don't have to write any code. If you want to do something more with it, for example, you want to actually use the value in your simulation for whatever reason, maybe you want to compute the maximum density at t equals 0, and then set the atmosphere value as a relative of that. So if I say I want the atmosphere to be 10 to the minus 10 of the maximum that's on the grid, means you have to first compute the maximum, then multiply the 10 to the minus 10, and then replace all the cells with densities less than that by that atmosphere value. That would be one way where you would actually need the value in the simulation. In Cactus, there is the interface that one uses at runtime to get access to these reduced values. And just as they were two different drivers, Bug and Kirkwood, there happen to be two different ways of getting this. The old one and the new one. Turns out that the newer driver, Kirkwood, supports the older interface only. And the older driver, Bug, supports the newer interface. This is basically a historical accident, I guess. Presumably one was implemented when Kirkwood already existed and nobody bothered to change it, or it's hard to do. I think it's actually hard to do. There is two functions that you can call. One is called CCTK, Cactus Computational Toolkit, reduce grid arrays. That is the definition of a grid array. And the older one is just called CCTK reduce, without anything in there, but also only acts on grid arrays. So for most of the talk, I'll really talk about CCTK reduce, because this is the one that you're most likely using in an actual simulation. This Kirkwood X is really still very new, and Bug is really old, but you certainly won't use Kirkwood. Right. The way that this works is that there are the various reduction operations that I had shown you. I had shown you them by name. This is not actually how the code would use them, because it's supported by both Fortran and Plus, ONC. You don't actually refer to the individual reductions by their name, but you get a handle and then you refer them by the handle. You get the handle that you want by calling the CCTK reduction handle function. That one then takes a string and it returns to you the unique integer handle for that particular reduction. That's not a compile time constant. It's not going to be the same every time because the different drivers can register what reductions they offer. And these are the ones that you can use. So this is dynamically determined at runtime to some degree. At least it depends on which driver you have. And the principal driver could change the order around. And what is reduction 0, that might be a sum today, might be a maximum tomorrow. Okay, so on that function, you get an integer back, and that's the one that you use. Once you have the integer handle, you can actually call the CCTK reduce function here. And you can see it takes a good number of arguments. And you can also see that it ends with the 3 dots here. So that ellipsis is being lazy. That is the C notation for a variable arguments function. Existing here can do a reduction not just on a single grid array at once, but can do multiples, which is useful because you reduce the overhead that you have in the system. If you want to do the reduction to get the center of mass, you actually have to do 3 reductions, one for the X, Y, and the Z dipole. And it's good to do them all at the same time because otherwise you pay the latency cost for setting up any API application. So, arguments that this thing takes, first one is something that you will very often see in any Cactus callable function, namely a pointer to the Cactus grid hierarchy. The AH, that's the CCTK-GH pointer that you might see every once in a while. That's basically all of Cactus's global variables. Then, divided by MPI, next argument proc is the MPI rank that will receive the result. Or you can put in -1, in which case this is the same as an MPI all reduced, which means that all the MPI ranks get the result. That until 230, yes. Okay. Third argument is actually that handle that I talked about. Make sure that you have the correct one. There's 2 slightly different flavors that you could use. If you give the wrong, you get an error message from the system. So at least you know. Then the next integer is the number of output values per input field. Sounds a bit silly, but I'm giving it 1 input field. I should only be able to make one reduction out of that. That isn't quite true. If you have a complex number, you might need 2 input fields to get 1 output to ask the output values. But for all practical purposes, this will be 1. Then Cactus supports multiple types of data on the grid. Typically, you would have a real value number because you do physics deal with actually real value quantities. But it could also be an integer. For example, you might have a flag that flag cells as being readable or in need of refinement, or you might still want to do a minimum and a maximum reduction or something like that. So it could be an integer. Since this is all C and there is no type overloading in there, you actually have to tell it what it is, same as you do in PI. Takes a variable type of val, which is set to either variable int or variable real, depending on what sort of grid function you actually delivers. There's a complex one. Yes, there is that one. And then finally, you will have a pointer to where you want to store your result. And because we don't know what type the input has, it could be an integer, it could be real, or it could be a complex number. You can't really use a type pointer here, so you use C's fits anything pointer and void pointer. So you have to make sure it's the correct thing, right? So this is where the result comes. Or the results. Then you say, how many input fields do you have? Do you want to do a reduction only over the density, or is it density X and Y and Z? And once you have that, the list of pointers for all the variables that you want to reduce. That's why this is dot dot, because it depends on however many. That's what you would do. One thing, never mind, not an issue. All right, so any questions going into this? And it's usually best to start with these by following an example. There is obviously documentation for this. Look at the reference manual, tells you exactly what this all is. They might even have an example. Best is usually to find a forum that already uses it to see how this is done, or maybe this tutorial and then follow that. Okay, so let me see. So one example, I want to do this, and this is basically all. The canonical example, we are going to compute a mass given a density, which I think you all pretty much how this is supposed to go. You take the density, we're doing GR, you multiply by the square root of the metric determinant to get a proper volume element, then you integrate it all up, then you get a mass. And that would be depending on what you're doing, if this is Newtonian physics, and you just have a funny coordinate system, then you actually get the real mass of this thing. I'll write it like this, and probably isn't going to be anything useful because I'm either missing a Lorentz factor or I'm missing all kinds of other things. But it is a mass-like object. Then code-wise, what you get is you get kind of a fragment like this. Okay? So here, the first line, I'm getting my reduction handle. Sorry. I'm getting my reduction handle for the sum reduction that I need to call to do an integration. I get a handle back, and as always, for the function which prints a value, check that that value isn't an error condition. All the correct handles are 0 or positive. So whenever a handle that you're being returned is negative, there was an error. You should at that point either do something sensible or abort the simulation. To abort the simulation, please tell the user what the error code is. Really annoying if your code aborts something is wrong. Should at least tell the user what went wrong. Please give them a chance. Once you have that, you have to set up all the other things that you need. So the variables in Cactus are addressed not just by their pointer, because the pointer would just be a bit of memory. If you have mesh refinement, there's multiple bits of memory that take up your mesh. The IRACs, that doesn't help so much. You don't want to pass a string around all the time. They're different with Fortran. You hand in an actual value to variable index that you can ask Cactus what it is. Say, okay, I want to know what's the numerical index for the Hydro density variable. That is the conserved rest mass actually in the Hydro evolution. And you get back an index, get that a number. You better check that that number is an error condition. Error conditions again are negative numbers. That could be that you had a typo and that this variable doesn't exist. I don't think it could be much else. Whatever it is, if you get an error, report the error to the user so that they know what the issue is. So you've got a handle for the reaction, but a handle for the variable. You need some place to store the result. Only going to be a single double. So we make a double variable. Hold on.
I forgot. Can you remind me if the GR hydro there is that the door name or the implementation?
I don't know on top of my head. My guess is probably, I would say it's the implementation name for public variables and it's running private. Same as it's for the output. That would be my guess. And that's a bit of a bit. Yeah, you might run into issues here. Usually, these two are the same. Cactus, you have a little bit of a class structure present, where you can define what's called an interface, basically a set of variables that you have. Then a Thorn can implement that interface. And where there could be an interface Hydro evolution implemented by the Thorn GR Hydro. Another Thorn, say called Asterix, can also implement that interface. It then must provide the same variables. And there could be two different plug-and-play Thorns that do that. For example, Carpet and Plug both implement the interface driver. So they have to have the same variables around. And then it depends a bit what you give there. You can also have variables that are not shared, do whatever you want. And if you want to address those, you need to know which Thorn it is, because not all the implementations will have that. Right. So for us now, we need a place to store the result. All that rest mass, and first initializing it so that it doesn't discriminate me. Obviously, it doesn't have the full counter that I expect, just something that I put in to keep the compiler. And I have everything assembled to actually call the reduction function. What we use, I give it this DKGH -1 so that all the MPI ranks are told what the answer of the function does. My sum handle that I've just obtained, I have an output value, always basically. It's a real value grid function. I want to store that one in the rest class variable. It could be an array, but the pointer to scalar is as good as an array of one number. I have one input field, namely density, and I pass in that one index. Call the function, get a return, check if the return value is an error. Again, negative is an error. do something with my result, for example, I can print a screen and tell the user the summation of all the type that should be dense is whatever it is. That's the actual executable code. Now you've seen in the how to write the front tutorial that in order to actually have your code execute, you have to schedule it somewhere inside of Cactus. Otherwise, it just sits there and nobody does it. It's like writing a function that you're not calling. So we have to add a statement to our schedule.ccl file to actually tell Cactus scheduler call the schedule routine. In my case, it was schedule. I give it a name. Always starts with the name of the thorn, so there is no name conflict because this is basically seek. There is no namespaces. So it says rest class underscore compute rest class. Where do I want to do this? Well, I'm computing a rest class. This sounds like it's doing something that I would want to do in the analysis part of my simulation. I'm not evolving anything, so I'll put it in the analysis bit. In analysis. I'm also writing it in the C language, so that goes in there. And I should give it some human understandable description of what it does, and it says it computes the rest class. And you saw that I skipped one. I skipped the one here where it says options global. This one is somewhat crucial. Normally, if you compute something on the grid, you're in local mode, meaning that you have access to the local cache of the grid. You can act on that. You can set variables on the grid, compute the right-hand side, you can do whatever you want with it. But you can't do anything to the global state of the simulation because you're only looking at that local. On the other hand, this reduction is a global operation. It involves the whole grid, and it must only happen once. If, say, for MBI ranks, one holds 3 patches, one holds 2 patches. I can't try to do the reduction on each of those local patches because 1, 3, and 2 doesn't work. Then this doesn't really match up. If I call MPI reduce on all of them, eventually I run into a different. It needs to be in global mode, which means it's going to be called exactly once per iteration. And it's going to be called, and a little bit on which schedule bit you're in, either with the minus refinement level or the course's refinement level. Which one it is depends a little bit on where you are. In analysis, it happens to be class 10. This is one of the dicier things of how to use Cactus, because if you do it wrong, you silently get the wrong answers. But keep in mind, global basically just means being called once per iteration with the first or with the last refinement level. Nothing else. There's no specialty in there. You still are in the whole pool of scheduled functions. You just get skipped if it's not your turn. Right. Any questions for any of this? Okay. So that's the basic example. And if you do it this way, it'll actually work the way that I've shown you. This is a workable way of doing it. In our case, this density is just a variable that your IDO finds anyway, so it's always around. We just do the reduction. It gets a little bit trickier if what you compute is only computed to be reduced. If I want to compute my dipole, probably there's nobody out there that already computes the dipole. So I have to do this myself. This one is a local operation, right? I have to take the grid point density multiplied by the grid point coordinate and put that value into a grid function. So now I have a global scheduled function that does the reduction, and I have to have a local one that computes what I want to reduce the integrand. So I need 2 at the very least to do this, and one way of doing it is to take myself a local function, which I'm just calling rest class equals to row, and schedule that. Doesn't really matter so much where I put it, but for example, in the CCTK post step bit, this one happens after every single time step. Just pick one analysis once, and this will work. This means that for each time step in the proper order, so that all this works well with mesh refinement, I'm going to compute my quantity that I want to integrate on the grid, and I'm going to write these values onto the grid. Then every once in a while, the reduction will come about when it's time for a proper refinement level, and we'll do the reduction and everything is good. This in fact works. It has two assumptions that you really need to compute the split function of interest, the thing that you want to integrate every single time. You can't try to be cheap and say I only compute this every second time or every 10th time, but I only want to produce output every time. This way lies lots of complication. So do it every time, otherwise you're going to get into trouble. You also, that might be a bit confusing, need to have sufficiently many refinement levels, sufficiently many time levels around for that variable so they can do interpolation in time. And the last one, you must be checkpoint as a consequence. We need to have enough time levels around to do interpolation in time for the following reason. Cactus interpolator is actually very flexible, much more flexible than what you can find in lots of other frameworks. But it also makes it a bit harder to implement on the driver side. Mainly, it lets you do these interpolations whenever you actually want. So if you have a course and a fine level, and the course level steps with a step size of 1, the fine level steps with a step size of 1/2, perfectly fine to call that reduction and time t equals 1/2. Here's the fine one. That's fine for the reduction of the piece of the grid that's the fine grid. But for the coarse grid, where there is no fine grid, you now have to choose. Do I either use the data that corresponds to t equals 0, or do I want to t equals 1? Either one is 1/2. If I want 1/2, I need to have both, and I need to average them out, or do an interpolation time to the t equals 1/2 time slice that could exist there. Does that make sense? That's the reason why you have to have multiple refinement, multiple time levels. One second order and time accuracy is these interpolations are on one side, and you actually need 3 levels if you have 3 unknown coefficients in a polynomial homology. So that means this gets relatively expensive for something that you really only care about output every once in a while. But that's the price that you pay. You could play tricks, and you could know that you're only ever going to need this one every 32 iterations when everything aligns nicely in time and only have a single time level. Can work, but you need to be careful that this is actually the case. Otherwise, you either get an import or you get wrong answers. So, can be optimized for that figure. Okay. And this next rather complicated plot basically is a description of what I just told you with my hands and words for the graph. Namely, you're asking for a reduction here on this t equals 1.5 time. You need to do an interpolation in time from the 2 coarser time levels, the black ones, down to that time. That's where this comes in. The next section here used to be of interest when we had a slightly different version of this talk, where I would go into more details about how you can actually avoid the extra storage and you actually control exactly when things get computed. That is doable. It requires that you use perfect internal macros, or perfect provided macros, such as this begin graph level move and begin map. That basically let you yourself go over the grid manually and put whatever values you want, and then you can do reduction and then you're good. This is still in there, but there isn't any example for this here anymore. I put that up well, so that we have 2 flavors. One that's a little bit easier to use because you only have to worry about the schedule, but you don't have quite so much flexibility. One version that gives you all the flexibility, but it also puts you in the driver's seat, so you need to know what you're doing here. All right, let's take what I kind of shown you and I'll put it all together into a single code editor. So, what we want to compute is now really a center of mass type quantity. So there's actually 2 types of integrals that you see here. The first one that says m_I. That one is the dipole, its density times the coordinate. And the second one, that's just the mass. That's the mass which is just the density times the volume. Then if you take your dipole, you divide it by mass, monopole if you want to, you get a measure of the center of mass. That's exactly how you would do this in your introphysics process. And if I'm doing this with the quantity hydrobase rho, then this thing is really quite the last. There's a metric determinant missing. If you do it with the geohydrodense, then it actually is. Either way, either case, it's going to be good enough for us to just tackle that. Then track a neutron star on your grid, for example, which is one thing you might want to do with this. And there is modules in one as do something like this, second trans volume interval and so on. There's this extra bells and whistles so they can track two blocks of matter or getting into trouble. But it is that principle. Okay, so this is somewhat similar to writing a new form. It uses a bit of a different technology to do it, but it's kind of somewhat similar. It also means that you can walk along it. Okay, so let me see how this works. Is anyone actually following along, or should I just talk and click? Okay, very good. So I'll talk slowly and click slowly. Okay, so first of all, we go into our freshly uncharged tar file, the Cactus repository, Cactus main directory. Let's use the sim factory. When you're starting off on a new system, on a new laptop or workstation, sim factory, you always have to run the setup silent first so that it initializes its own internal configuration files and it checks, do I know this system? Do I have to do anything special? To run this one, what should happen? It should say that this is the Turing machine, and it writes whatever it needs into the desktop.ini file that you all will be familiar with because you have to put your cluster allocation names in there. Right. Now, there's a bit of trickiness in here. As you can see, there's pattern code. The Cactus build system, the make file that I had shown you before, has a couple of pseudo targets to make new thorns. One of them is called new thorn, which then enters into a dialog view to ask you what's the name of the thorn you would like to create. The author, where do you want to put it? So it asks you lots of questions. This tends to not work in Jupyter because you can't answer. So instead of, you have two options there. You can either prepare basically a file with the inputs as you think they should be there, just type that file in, that works. This one here tries to be a little bit more flexible. It tries to set up a little challenge response type algorithm where it has a couple of challenges that it expects from the script, for example, the challenge for name, which will respond by the word center of mass. And all these others it will go through, but in the end, it will have answered all the questions. This is just trickery required in the notebook. Obviously, if you're doing this on your own in a terminal, not by Python, just answer the 10 questions. Right, so let me run this, and this should have now created a new form. Right? As it says, it's creating norm center of mass in the arrangement Einstein analysis. It also reminds me that I should fill out the README file and the documentation. Right, so let's see. Three files need to be written: interface.ccl, arm.ccl, ghetto.ccl. These are all just provided as a blocks with the right file. 10 minutes or so, then question, yeah. Let's see what we get. So this is the, would be very similar to
10 minutes.
when you wrote the thorn, you give it a name, or actually tell it what it implements. It implements the center of mass interface. It inherits from some other implementations. Maybe it inherits from grid to get your coordinates, and it inherits from hydrobase to get access to the density. This one we don't need, ignore that one. And then it defines a couple of helper grid functions where we store the center of mass. So it has a center of mass grid function group, grid function, and has 3 time levels, 3, and there's 3 of them, x, the y, and the z. Okay. It also, just for the take of it, declares a couple of different scalars, the numbers that live on the grid and that are known to Cactus that you can output this. For the actual mass, x, y, z component of the center of mass. Okay. Press enter, right, and put 1. Similarly, for the schedule, it turns on storage for my bit function that you actually have memory. You just declare them, but I don't always need them. Just press them on, give them memory. It ensures that whatever I'm reading from hydro-base row also has memory. Otherwise, you get a sec call. This is where you get undefined values. And it schedules two functions that I had talked to you about. This is pretty much what I had shown you. With the extra annotations for the reads and writes, which for the sake of this, probably can't basically. It should be there, they're nice. Yep.
If two different forms are used row, you initialize storage in both of them, what happens?
Okay, so the question for the remote audience is what happens if more than one Zorin contains a storage statement for the same variable with different numbers? And the answer is the largest memory wins. You say I want at least 3. If somebody says I want at least 5, then 5. Okay, so 2 scalar functions. Wait, this one. This one is boilerplate. Actually, it's not even required to use interpret anymore. And then we've got the source code, which implements essentially exactly what I had told you before. Will be an actual loop over the grid, loop 3 off, that loops over the grid. If you're familiar with performance portability frameworks, there would be such a loop. This is nothing as fancy as that, but it goes a little bit that direction. You can, with certain forms, get a bit of optimization here where it will do tiling and threading in here. But basically, it lets you loop with just this one command over the whole grid. You give the loop a name, so it gets a nice error message. It's, compute center of mass, local compute. It wants the ever-present CCKGH, and it wants you to tell it what's the name of the X, Y, and J index, X, Y, and Z index into the grid, the IJ case. And then you have a regular Cactus type thing. You compute the linear index for the GF index 3D function, and you index your grid functions by an index, putting whatever else you want to have. And so you can see it's density row times the coordinate X, basically, times Y, Z. And then you can close that looping macro to have everything repeat. Does this look somewhat understandable to everybody? Okay, good. That's the local piece. That's just that's the good function that we want to reduce on. We have a global one then, center of mass global, which we will schedule in global mode to do that reduction. You can see this is a little bit longer, but for the most part, what it does, it's hand, that's summation hand here. You get the hand into my various grid functions, the density that I want to integrate over, the center of mass helpers, X, Y, and Z. And then it calls the reduction for each of them. Which I'm doing it this way. If I just copied and pasted the code, I could have made one reduction for all 3. This does 3 reductions, get the reduction value for each of them, and it stores them in the corresponding grid scalar. X, Y, and Z. Grid scalars, because they are on the grid, they will be an array of grid scalars.
5 minutes, please conclude.
I will. So I now have my reductions. I have to do my division, get rid of the overall scaling of the mass. Now I have my center of mass that I can store in my grid function and then do something with it. But clearly I must be doing something else with it because here it's just stored, I would never see it again.
What does star mean? Star, scalar.
Yes, it's an array X, that's for 0. That's the quantity reference. The principle, these grid scalars could be an array of grid scalars. There could be 10 by the same name. The first one is scalar bracket 0, the second one is scalar bracket 1, and so on and so on. If there's only one, well, it's just a pointer, and you can put a star in front of the reference pointer, or you could put bracket 0, and it makes no difference to the compiler. It might be something where you won't be explicit whether it's just a pointer to a single object or it's the first element of the array. It looks a little bit funny. Unfortunately, you wouldn't see it because Fortran always did pointers anyway. Okay. Any more questions on this? Okay. Then the humdrum files. I've written my source code file. I need to compact it. Either. Let me work with that. And that's it. That's my new thorn. In kind of a rapid go-through mode. And I can now compile everything. Again, Python trickery to actually add my new thorn to the thorn list. Open an editor, add it to the end, call it a day. This is not a human, so it gets some Python code. And then compile this thing. And this should now look hopefully a little bit familiar. Yeah. Yeah. It's doing its thing, it's creating these various auto-generated paths, it's trying to compile them. And hopefully it's not going to compile anything but our new form. That's the only thing that really changed. While this is compiling, while it's maybe also compiling for you, I'll just show you something that you should always also do. You should always write a test case for your new code. If for no other reason you want to test that your computation is correct, once you have that one, you might just as well take that one and turn it into a test case so that others can afterwards check that there was no introduced regression.
2 minutes.
This one shows you how you can do that. Gives you a bit of an introduction what the test case should be. A test case should, well, actually test the proper physics, obviously. It doesn't have that's correct. That's test regressions. It should be quick, it should be small, and it should be reproducible, I guess. So don't write a test case that runs for half an hour, that's not super useful. Don't write a test case that the cluster, run it. Write a test case that runs in 30 seconds or so at most, better 10 seconds, because we have about 300 test cases. Test case that moves right in here actually. Test parameter file. And the important thing is that you need to run it. Yes, so there isn't much else other than that in there. Let me check.
1 minute, please conclude.
Okay.
30 seconds, please conclude.
So there we go. The long linker line. This apparently contains the kitchen sink. And then this is basically it. I'll let it run everything below because I think at the end it shows me some answer what it actually concluded, but I have to do the intermediate steps. So that's pretty much it as far as writing that does. And it gives you a bit of an idea how you can do this. Do you have any questions for any of this while we're waiting for this to finish? take that.
How would you do, you set up in this code that, add all the views online?
The first question was how I would add all three in one line instead of calling 60K reduced string lines.
Yeah.
But the way you would do that is by adding only variable indexes as the variable arguments to the function. So I'll show it here, for example. So what you want to do is you then declare yourself an array of outputs. You know, two words now, two of them. Then this one here is the number of output per input, is one. But now I have two inputs. And I'm not just going to store it in that single scalar, but I'm going to store it in my outputs array. Then it would say I, and then I. That's what it would look like. And you could put all of them in there. And I strongly suspect I just only gave it to probably a case.
Yeah.
But in principle, you should do it this way because it's less work. Okay. Any more questions?
Not a reduction, which I don't think question. Yeah,
Fine, Roland, what's going on?
So when you do like the 2D output of carpet,
Yes.
how does it determine which slice take output of?
Okay. When you do 2D output, whenever it does output, it only outputs those refinement levels that exist at that particular time. So if you look at what you get for 2D output and you ask for 2D output in the equatorial plane, okay, then you would start off at t equals 0, where all the refinement levels align, and you get all the output for everything. Then you have first iteration, iteration 1, where now everything except the course of the finest one out of sync. So you get exactly one output for the finest refinement level. Then for iteration 2, the finest has caught up with the next the next course. So when you get two outputs, one from the finest, one from the next course, and then it goes through. So it does not, when you ask for 2D output, do the interpolation in time. It only does that when you're doing the interpolation and the reductions. So the interpolation will do it if you were to ask, what's the value of my variable rho at coordinate 3 pi 16? It'll do interpolation in time if it has to, if 3 pi 16 happens to be not on the refinement level that exists at that time. But not for just output.
So here you have -1 for the which is all of them. If you choose a specific core, does the pointer output just become null when you can't use it on certain cores?
So the question is, what happens if I actually request output to be delivered only to one particular MPI rank rather than all of them? And in this case, it doesn't change the pointer, because this is C, everything is always passed by value, but you could pass null for the pointer. The pointer doesn't have to be valid. It inherits the semantics from MPI reduce.
So after this, so say 1.40, but this code is then run on a different MPI rank, output wouldn't point to anything after that, or no?
Output still points to something, just the memory location that it pointed to still has its own value. So in my example, I initialized my output with 42. On the ranks that are not receiving the result, this would remain 42.
Very generic question. I've seen those 4 lines of code, EI equal cert, IR equal the cert. I mean, it's all obvious when we're looking at it. You can reduce it to 2 lines. Why do we always define these future variables? Say a cert are index greater than 0, for example. Combine the top 2. EI equals blah blah blah. Cert EI greater than 1. Cert K-bar index greater than 0.
Or you want to put it inside
Yes,
the,
sir, yeah. Uh,
I think it's dangerous. If you set the ndebug undefined, then the assert becomes a no-op, and I'm no longer sure if the standard would guarantee that its argument even get evaluated. Right, so if you were to change this one, it's going to give you a warning from the compiler anyway. You change it to this. This is what you're thinking of.
No, BI is not necessary at all. Rid of BI.
So I need the value to the whole there. Need the value. Not doing this to another. Okay.
This is K-bar index greater than.
I need the value. But VI shows up here.
Oh, crap, you're right. Right.
But even
Yes.
what I showed you there,
The reduced stuff, that could be, that, the bottom one.
yes, but then my same argument applies. I'm not sure if the C standard actually guarantees you that if you define no debug, people have done so because they want to get that last percentage performance that you possibly get by removing your asserts. Doesn't turn this thing here into a situation where the argument to assert is failure. So I would advise against it. All right, any more questions?
Thanks, Roland. I can see you. We have about 8 minutes till 7 minutes, 22 seconds, I guess, until our next presenter, who's going to be remote. And this is our lightning talk. So it's only 30 minutes. I don't know how many minutes we've allocated for questions. Like, 5, okay, 25 plus 1. Great. So, great. Can you make sure, can you try saying something to make sure we can all hear?
Hi.
Wonderful. I think we can hear each other. That's great. Yeah, I recommend it if you can to put yourself in full screen mode. You don't have to, of course, but it'd be nice. But yeah, so we have Kusan Alibekov who's going to be giving us a lightning talk, 25 minutes talk plus 5 minutes of questions. And the topic is, looks very interesting, black hole imaging by using relativistic ray tracing techniques. So please go ahead, Kusan.
Hi, my name is Husan. I am second year master student at National University of Uzbekistan. I am also working as a junior researcher at Ulubek Astronomical Institute located in Uzbekistan. My topic will be black hole imaging by using relativistic ray tracing techniques. I will give you some brief introduction to my work and my research. We know that black hole imaging is a more popular research area in the astrophysics. From the 1988, people like Luminant have tried to create some simulation using some computational methods, but you can see that in the top right of the image, this image is the first simulated black hole image created by Luminant, and after that, 2016, the computer simulation of black hole has been created by by the researcher, and after that, we have observed there has been created the first observable image of the black hole created by the Luciano and observed by the team of the Luciano Razzola. And what is important we have some assumptions and requirements to make some simulation in order to make a picture of the black hole by using relativistic techniques. We have to set up some requirements like in our research, the most important things is that the model of accretion disk, like we are using in our work the Novikov-Toron accretion disk model, and after that we have to take into account of some effect of the general relativity and of other gravity effects. I mean that we need we have a space-time, and we have to know about space-time geometry and function of symmetric parameters, and we have to know how to implement these parameters in the code and other things. In general relativity, it is important to solve the geodesic equation and to analyze and to learn the motion of the particle around the black hole. And to do this work, we will use we have to solve the geodesic equation, and we know that every particle around the black hole moves geodesic line, and after solving this equation, gave us some important properties of the particle, and we know about the more about black hole, what's the effect of the spacetime and other things. After that, after solving geodesic equation, solve the geodesic equation, we have to set some initial conditions for the photon. I mean that to create a black hole image, we will learn the motion of the photon around the black hole, and after that, we will take the picture. To do this, we have to set initial conditions, and in our code, we will use some numerical calculations. We will do some numerical calculations. I mean that we will use some numerical approach like Runge-Kutta method to solve to solve the differential equation, and we will use also numerical integration, numerical derivative techniques, and other things. After that, I will talk about the result and our future prospects. What we do in this, what's the meaning of using the ray tracing techniques? We have a black hole, and as I said before, we will use some model of the accretion disk, and in this model we are using the thin accretion disk, and it's called the Novikov-Toron accretion disk, and we have a screen located far away from the black hole, and we will observe black hole from the some inclination angle, and the general approach to do this more in the modern, in the general relativity, we have to learn, we have to calculate the motion, we have to calculate the motion of the photon coming from the black hole, and we have to do this from the other approach, but in our case we will use some opposite direction. We have a screen, and after that we will say that we will send some photon to black hole from the screen, from the observer screen, and we will calculate that how many photons are falling into black hole, and after that we will get some point of the photon in the screen, falling into black hole, and some photons are escaping from the black hole. And in our case, we are using this approach, and after that we will get the image of the accretion disk in the screen, like on the on the right of the image. And we have to say that our observer space-time is a flat. And we have a two angle to calculate the black hole image. First, there's a viewing angle, and it means the inclination angle. We are observing the different position, and how can this affect the image. And after that, some photons are coming from the black hole, and it will be some approach. We don't know in our case source is where is located the source of photon. We are observing just like the photons coming from the black hole, and in this case it should be investigated the emission angle, and after that we will take the we will do this some step size methods and other things. We will use as I said before, we will use Novikov-Tor model. Novikov-Tor model describes the accretion disk should be in this case geometrically thin and optically thick. And in the Novikov-Tor model, we have some parameters. I mean the black hole mass and the black hole spin parameter and the mass accretion rate. And in our case, viscosity parameter does not affect very much into structure of the accretion disk, and we will not consider in the code viscosity parameter. What will get after the creating simulation of after simulating black hole? And in 1978, Luminet have created the first simulated image of the black hole. He have observed he saw that the high order image of the photon, and in the left of the black hole, we will observe the Doppler effect, and in the center of dark area is called the black hole shadow. This is only from the this is only primary image. I mean that it should be considered some secondary image, and in our work we created the full image of the black hole. I mean the ghost image and the secondary image. In the Novikov-Tor model, there is some assumptions, actually 10 assumptions for Novikov-Tor model. First one is the spacetime should be stationary and axisymmetric and asymptotically flat. And second one is accretion disk should be non-self-gravitating, because if the accretion will be self-gravitating, we can't we can know how the effect of our gravity, and we will get some wrong results related to our expectation. Third one is it should be accretion disk should be located in the equatorial plane, and the disk should be perpendicular to black hole. What does the mean of the black hole? We know that in the black hole formation, as we described the supernova after collision of supernova, spin will be perpendicular to accretion disk of the the accretion accretion disk of the supernova. It says it's like that. So fourth assumption is the inner edge of the disk should be located in the isco radius, the innermost stable circular orbit. And as we said before, accretion disk should be geometrically thin. What that means? There is some angle between we are observing this. Accretion disk should be thin, and h/r should be less than 1. In this case, it will be thin accretion disk. After, in the case of Novikov-Tor model, all particles should be follow the geodesic line, geodesic orbit in the equatorial plane. And in our case, we are not considering the magnetic field, because if we consider magnetic field, it will be more challenging to calculate the motion of photon coming from the black hole. In the case of magnetic field, there will be other impact. In Jeremy-Schmidt simulation can calculate will include the magnetic fields. In our case, we are not considering magnetic fields. Last one is not much important. So we say that space-time space-time is important. So metric and space-time geometry is important because according to general relativity, it will be some effect. We have you have to know about gravitational lensing, gravitational redshift, and percolation of the percolation method, and these three things will predict the Einstein gravity. Einstein theory is correct, and in this case, in the curved spacetime, it will be always all photon coming around, moving around the black hole will be bent. And in our case, we assume that stationary axisymmetric and asymptotically flat spacetime. That's a general case, and after that we can choose whatever we want. Like I will show in this for Kerr metric, and we can calculate for non-Kerr metric and other things. In our code, we can calculate all spacetime geometries, and we can change the metric, and we can get different image, and we can give some calculations about spacetime. In our case, geodesic equation will be like this. We have to, as I said before, every particle follows the geodesic line, and we will get some equation from the geodesic equation, and we will get r dot, phi dot, and other parameters. And to solve the geodesic equation, we have to set first the initial conditions. In our case, we have an accretion disk, and we have an observer, and we are observing from some inclination, from some distance, and we are observing some inclination with the inclination angle, and we have a source like corona. Is a photon are coming from the corona, and reflected photon we are observing the reflected photon from the corona, and this is a general case for us. And we can set the initial conditions in the code, and we implement all parameters with the, I mean, this the vars 0 is a distance between the between the observer and the accretion disk. And vars 1 is the theta angle theta, and in the case of vars 2 and vars 3 correspond to sort, and I mean it's related to t dot, and this phi dot, After that, we have to do some numerical calculations. To do that, we will use some methods. First one is first order Runge-Kutta method. We will use this method to solve the geodesic, to solve a differential equation. And in our case, what we observe is we are challenging the speed of the code. So we have used some interpolation method to make code faster, and to do this we have used the Lagrange polynomial interpolation. We have used also some numerical differentiation and integration to calculate the flux of photon coming from the black hole, and all equation of the flux and redshift and as gravitational redshift has been given in the paper written by Cosimo Bambe, and we have used also Asghar Abdikamalov papers related to X-ray data analysis. And two examples numerical integration, we have used some Romberg integration, Gauss quadrature integration, and other things. After that, we have an image, and in our case, what I am going to show in this picture, we have implemented all code separately, because in this case our code is working fast because it will be difficult if we add all code in the one file. So we have separated all files. I mean we have implemented all spacetime parameters in the one C file, and all other things, and we have opened the new file to set initial conditions. We calculate the geodesic equation in other C file, and we have used. We have also separated. We have also added some numerical integration files like Gim and F.
Can you hear me? You're now in your question and answer period. You have 5 more minutes to wrap up, and yeah, just want to let you know. Thank you.
Okay. I am going to present the result and our future prospects. We know that this shadow of the black hole from this all correspond to first one is has been observed in inclination angle equals to 85, and we are observing from higher inclination angle, and we will see the image. We will see shadow like this. If we increase the spin, we will get some distorted appearance of shadow. If we consider the spin equals to 0, we will get for Schwarzschild case. In the case of after that, we can change the spin parameter with corresponding changing with the inclination. For different inclination angle, we will get different image. in the case of if we spin parameter equals to 0.9 or smaller than this, we will not get the distorted shadow. We will get some like circular shadow. And in the case of Novikov-Chorin limit, we will get some distorted image of the black hole from if we inclination angle equals to 85. Other case, we will not get distorted image. And after that, we have implement the code to create the accretion disk of image. We have assumed that the inner edge of the accretion disk located in the ISCO and after outer radius of accretion disk is equals to approximately 25 solar masses. And in the top panel, we will get for primary image. I mean this ghost image. We have calculated only coming from the black hole, and we are not considering the returning photon around the black hole. In the second image, we are including the effect of returning photons, and we will get some pictures. After that, we have tried to plot the gravitational redshift, and we have get some image from the. It will be. We have changed the parameters, spin parameter, inclination angle, and
You have 1 minute.
other.
Please wrap up. Thank you.
Yeah, it's check this in the left panel. We will get the primary image. In the right panel, we will get secondary image. After adding this image, we will get full image of the black hole. In this case, if A equals to 0, we will get Schwarzschild case. It's this is some coding problem because we are not taking clear image. There is some mistakes in our. It is related to length of the coding time, and if we get some parameters more accurate, we will get more clear image like in the above. That's all. Thank you.
Great, thank you very much. Not have any time for questions. If you do have questions for him, I would encourage you to use the chat functionality on the Zoom session. We now have a 30-minute coffee break. Thank you very much.
Thank you.